Fan, okay. I'd like to begin with a little bit of remedial Floer homology. I know we've already seen some of it in Zoltan's talk and already seen some of it in Tobias's talk. But I just want to first give you a little picture of what Floer homology is. I don't know if you've had this picture yet. So the basic idea of Floer homology is to imitate Morse theory. In Morse theory, you have, if you want to calculate the homology of a manifold, if you want to calculate the homology of the manifold, you calculate it. What's that? Okay, is that better? Is that the same? Or I could just talk louder. Okay, so in Morse theory, you have a Morse function on a manifold, and we know that from the set of critical points, we can reconstruct the homology of the manifold. That is to say, a chain complex for the manifold can be gotten as a free abelian group generated by the critical points of F. And we can define a differential on this where the boundary of X counts. So let's say this is the circle. We got the Morse function. Here we have 4 critical points. X1, X2, Y1, Y2. And the boundary of X is going to be the sum over all other critical points on the manifold of the number of gradient flow lines which connect X to Y, modulo translation, times Y. That is to say. So this is a chain complex which describes the homology of the circle. And what we notice is that we have this critical point x1, and there's a gradient flow line that connects it to y1. Well, in fact, there's a whole real parameters worth of gradient flow lines. So remember, a gradient flow line is a function gamma from R into the manifold, which satisfies the gradient flow equation. Gamma dot is equal to gradient of F at gamma of t. Maybe we want to look at downward gradient flow lines. And of course, there's a real translation action on this moduli space of gradient flow lines. If we divide out by that, so that is to say, I have one gradient flow line that goes from x1 to y1. Well, I can also translate it by any parameter and get a different one. So if we divide out by that translation, there's a unique flow from x1 to y1. So we see in this picture that the boundary of x1 is going to be one copy of y1, one copy of y2. And by the way, I suppress all signs and always work mod 2. The boundary of x2 is similarly going to be y1 plus y2. The boundaries of y1 and y2 are trivial. And so what is the homology of this? We see that x1 plus x2 is a cycle, right? Because the boundary of x1 is y1 plus y2. The boundary of x2 is y1 plus y2. So x1 plus x2 is a cycle, and y1 is a cycle modulo boundary. So the homology here of this chain complex is a z up here and a z down here, which is all fine because the homology of the circle. So this is what you learn from reading Milner's book on Morse theory. But now, a question you can ask is, okay, so Milner's book on Morse theory gives you this formula. It says that this is a chain complex that you associate to a manifold with a gradient. So in order to make sense of this, we have a notion of gradient flow lines. For that, we need a metric, and we need a function. So we have some data associated to a Riemannian manifold and a function. And we can associate to that this chain complex whose homology calculates an underlying topological invariant. But now you could ask the question of how do you know that this is a differential? So why is this? So we know it's a differential because it's the differential whose homology calculates the homology of the manifold. But if you didn't know that, just abstractly, why is this a differential? Now there's a very beautiful picture of this. And this is it's a classical idea from Morse theory. And the basic point is that you look at gradient flow lines that connect X to Z, and you suppose that we have a one-parameter family of those. So I should say that typically spaces of gradient flow lines can be large dimensional. Like, for example, consider the round sphere. There are two critical points, x and z. The space of flows that connect x to z is actually a two-dimensional space. So we really want to sum over those y's for which the dimension of this moduli space mxy is one-dimensional. And now the basic idea of why this is a chain complex is the idea that if you look at spaces of flows from x to z, which are two-dimensional, so they're one-dimensional when you divide out by reparameterization, and you look at the ends of this space. So what can happen to one-parameter families of gradient flow lines in a manifold in general? Well, what can happen is, and let's just draw a picture. What can happen, for example, is here's a one-parameter family of gradient flow lines. They can start to get stuck at some intermediate critical point. So suppose that the dimension of the moduli space mxz is 2, and we look at the ends of the moduli space of mxz modulo translation, then those ends look like, so for one parameter family, this dimension is 2, I look at a one parameter family of gradient flow lines, eventually they'll get stuck on some intermediate critical point. That is to say, the ends look like a disjoint union over all y's, such that over all intermediate y's of a moduli space that flows from x to y mod r times the moduli space of y to z mod r. With the property that the dimension, so this is y such that the dimension of the space of flows from x to y is the dimension of the space of flows from y to z is 1. So this is a basic property of how one compactifies gradient flow lines. One parameter families of gradient flow lines get stuck on some intermediate critical point. And now, if you just remember that the number of ends of a compact one manifold with boundary is always even, then you see that this number of ends is 0, at least mod 2. And today we're always working mod 2. And on the one hand, on the other hand, this is also the z component of d squared of x. So this, on the one hand, we know this is equal to 0 just by abstract nonsense. On the other hand, observe that this is the z component of d squared of x. So we've just proved that d squared is equal to 0. This is an independent proof that d squared equals 0, which uses only the compactness properties of gradient flow lines. Okay, so Floer's great idea was that one can apply this kind of idea in other settings where it's not a finite dimensional manifold you start with a Morse function in which you already have a notion of, I didn't write enough symbols on the blackboard. So this is the, let's call this the Morse complex of the manifold. And Morse theory says that the homology of the Morse complex is isomorphic to the singular homology of the underlying space. So Floer's wonderful idea was, suppose that you have some infinite dimensional setup where you don't have a manifold and can't make this kind of conclusion. So you're not looking at the singular homology of anything that we know of. But we have another setup in which we have spaces, these generalizations of moduli spaces of gradient flow lines that satisfy the same kind of compactness properties. Then you fake it. You just write down this complex. Hopefully d squared is 0, take its homology, and hopefully you get something that's independent of whatever auxiliary choices you made. That's Morse theory. That's Floer homology in a caricature form. Now, so we're seeing now many examples of Floer homology. In the examples that we see, the thing that plays the role of these gradient flow lines are holomorphic disks. So let me, before going on into sort of Heegaard Floer homology and sort of higher dimensional cases, let me just talk about a one complex dimensional case. Let's suppose that we have a pair of curves in the plane, L0 and L1. Maybe I should use colored chalk technology. L naught, and here's L1, let's say. And now we're going to look at the Floer homology, which is going to be the free abelian group generated by L naught intersect L1. Okay, by the way, throughout my lecture, Z will denote the field with two elements in it. Okay? And the differential of X is going to be the sum over all Y of the sum over all Whitney disks. So, I mean, I could say moduli spaces of holomorphic disks that connect X to Y modulo translation times Y. This I could say, maybe that's the better way of saying it. So that is to say, now we're looking at holomorphic disks. That is to say, maps U from the standard complex disk with I minus I marked, which map into our plane in such a way that the left arc goes to L naught and the right arc goes to L1. The I gets mapped to X and minus I gets mapped to Y. So the space of such maps with these kind of boundary conditions are called Whitney disks. And we're looking at holomorphic Whitney disks. For example, in this picture right here, we're looking at, let's let this be X, let this be Y. We're just looking at holomorphic disks that map into this region over here that send the left arc to well, I guess in this case I've changed my blue and my white. The left arc, in fact, why did I not? So the left arc gets mapped to the white, right arc gets mapped into blue. And how many such disks are there? Well, by the Rema mapping theorem, there's essentially a unique such disk up to translation, right? I map I to X minus I to Y, and this space has a one-parameter family of automorphisms, and if I compose by those, I get the various disks. I divide out by that action, then we see there's a unique holomorphic disk that goes from X to Y. So in this case, our chain complex looks like X and Y, and there's a single differential that connects X to Y. There's nothing that goes from Y back to X, because the obvious disk that you see right here is not compatible with the orientation. So there's a disk that you would get which maps the left arc into blue and right arc into blue and left arc into white, but that's orientation reversing, so it has no holomorphic representatives. So we see here that we've got a chain complex whose homology is trivial, okay, which is good because this pair of curves is isotopic to this pair of curves, which have no intersections. So what you want is a theory that's going to be independent under sort of suitable perturbations, and this is a sort of suitable perturbation. So that's one point. And now, well, what goes wrong? So let's consider this pair of curves, X, Y. So, can anyone tell me what the differential of X is? What? It's Y. Can anyone tell me what the differential of Y is? X. Does anyone see anything wrong with this picture?
What's the grading?
Well, the grading is going to be, you see, if the grading is given by the dimension of the space of flows. So in both cases, there's a one-dimensional space of flows from X to Y. So this is going to be a Z mod 2 graded theory. But what else do you see that's wrong with it? D squared is not equal to 0. So let's investigate this proof that D squared equals 0 in the case of holomorphic disks. So what we want to say is that if we have a one-parameter family of holomorphic disks that connect X to Z, that the only kinds of ends that can occur is that we can pinch at an intermediate critical point y. So this is, so ends of moduli spaces of flows from x to z should correspond to ways of breaking up these holomorphic disks into pairs like this. Let me give an example in which d squared equals 0 and which illustrates this point quite nicely. And that is the broken heart example. If we consider this chain complex, then we have x, we have y1, we have y2, and we have z. And unfortunately, I've erased my conventions, which went into blue to, I guess, well, we'll have a new convention for every, oh well. Okay, so what is the differential of y1? Z. Is it z or is it x? It depends on which convention we're taking. If we take this convention, then it's z. Okay, let's do that. This may have been different from what you just drew. I hope, well, oh well. So the differential of x, the differential of y in this convention is going to be z, right? And what's the differential of y2? Right, maybe I should, why is the differential of y1z? It's because there's this holomorphic disk, right? Now, what is the differential of y2? What's that? It's also z, because of this, right? And the differential of x is going to be y1 plus y2. And now, what is our proof that d squared is 0? Well, evidently d squared equals 0, right? So, because it is. But what's the geometric proof? The geometric proof asks us to look at the space of holomorphic disks that connect x to z. That space of holomorphic disks is two-dimensional because there's an additional parameter which is you can cut. You cut into this heart like this. And there's a Rema map from the standard disk into this broken heart. So for any length t, you can construct a Rema map from the standard disk into here, unique up to translation. Okay, is that clear? And that'll give you a holomorphic disk with the suitable boundary conditions. But if this cut parameter goes all the way out to the boundary, then in the limit what you get is a flow from x to y1 composed with a flow from y1 to z. That's if the cut parameter goes out to here, but alternatively you could have cut in this direction. If you cut in this direction, you get the other broken flow line. So we just see that we've just constructed a moduli space, one of whose boundary components looks like this and the other boundary component looks like this. Is that clear? Paul's nodding enthusiastically. I guess you've worked through this before. I hope, all right, well, there you have it. So let's look at this example. Where does the proof that d squared equals 0 go wrong? What goes wrong is that now, once again, so how would we try to prove that d squared is 0? We look at moduli spaces of flows from x to x. That is to say, we want Whitney disks which map the top arc into x and the bottom arc into x as well. Well, how can we do that? Well, again, by the Rema mapping theorem, what we do is you cut in here however long you'd like, right? And you get a holomorphic map into this slit region. And again, this is a two-parameter family because you get to make this cut parameter as long as you like, and you have a one-parameter family of automorphisms. And you see that one end of this moduli space occurs when the cut goes all the way through. And that's the composition of our flow from x to y with our flow from y to x. But there's another end of the moduli space. What's that? What? We don't cut at all. And when you don't cut at all, then you don't get a Rema map like this. You get a very special kind of map, which is a map from the disk into our space, all of whose boundary lives in one of the two subspaces. So we were asking for disks which mapped the right arc into one of the subspaces and the left arc into the other space. And we see that this two-dimensional moduli space has two kinds of ends, one of which was this nice end that we talked about earlier, but another end is this weird thing, which is just as a single boundary component. In fact, it's usually convenient to think of this as a juxtaposition of two maps, one that looks like this, except this is a constant map. So what we see is that there's a kind of splitting off of a holomorphic disk. This is actually a picture that came up in Tobias's talk, but maybe here's a very concrete way of thinking about it. So, in other words, there are problems with setting up Floer homology in the case where you allow holomorphic disks with boundary inside entirely inside of one of the two Lagrangians. Okay, so is all this clear? Are there any questions? Okay, so this was a sort of crash course in the basics of Floer homology, and now we're back in our in the Heegaard Floer world. In the Heegaard Floer world, we equipped our three-manifold with a Haggar decomposition. That is to say, we had our Riemann surface, we have a G-tuple of circles alpha 1 through alpha g, we have another G-tuple of circles beta 1 through beta g, and we have a reference point z. And we can now look at the G-fold symmetric product of sigma, which is the set of unordered G-tuples of points in sigma, which actually even surfaced again today in Ron's talk. And we have this pair of Lagrangians, T alpha, which is alpha 1 cross up to alpha g, and T beta, which is beta 1 cross up to beta g. And now, as Zoltan said, to get an interesting theory, please.
So in your play examples, you gave us several families, but how are we to know that there's not more working?
Sorry, how do you know? I'm sorry, what was the question?
So you said here's this two-dimensional thing, so the grading looks like this guy at the top, two in the middle, one at the bottom, but maybe there's, a third, some other dimension you could go. How do we know? How do you rule out how to use a larger canvas? Where do you?
Okay, so.
Is it supposed to be out from the combinatorics? Because I didn't see.
No, it's not supposed to be obvious from the combinatorics. So okay. Actually, let me come back to that point in a moment. Let me just first write up the chain complex, and then we can talk about it. So we have our alpha tori, we've got our beta tori, and we choose a reference point z. And there's now a chain complex CF hat of y, which is the free abelian group generated by intersection points between the alpha and the beta tori. And the differential of x is a sum over all other y's times a sum over, let me say it this way, pi 2 xy. I can't remember, did Zoltan introduce this notation pi 2 xy yet? Last talk? Okay. Okay. It's meant to be homotopy classes of Whitney disks. Homotopy classes of maps which send the left arc into T alpha, the right arc into T beta, this to x and this to y. Homotopy classes of maps like this, that's pi 2 xy, and we look at the number of holomorphic representatives for that. And then we don't look at all homotopy classes of maps, but we look at those whose intersection number with the subvariety Vz is supposed to be equal to 0. So remember, Vz was the subvariety, which is z cross sim g minus 1 of sigma. That is to say, it's g tuples of points on sigma, one of which is our reference point z. Okay? Now, so the statement is that this is a chain complex. So that was your question, right? So why is this a chain complex, right? Is it?
No, it's how to compute the dimension of m.
Oh, okay. So, all right. So then let me, rather than answering your question, come to this question of why is this a chain complex? So, too bad. So this is a chain complex. The way one proves that this is a chain complex is, once again, one looks at two parameter families of flows that go from x down to z. And I'm not going to go into this at all, but let me just say very briefly that there's a Gromov compactness theorem for holomorphic disks. And in the Gromov compactness theorem for holomorphic disks, it says that if I've got a sequence of holomorphic disks with these kinds of boundary conditions, they're going to limit to a suitable holomorphic, to arrangement of holomorphic disks. So any one parameter, ends of a moduli space of holomorphic disks from x to z are going to be modeled on either getting stuck in an intermediate intersection point, or there are these other kinds of ends, which is that we can bubble off a disk with boundary inside of one of the Lagrangians. That's the example that we saw in the plane earlier. Or there's another kind of end that one can in principle have, which is that spheres can bubble off in the middle. So what one needs to do is one needs to prove that none of these things exist. And indeed, in our case, one can prove that, first of all, if a sphere bubbles off, then you get a holomorphic sphere in the G-fold symmetric product of sigma. But we looked at things whose intersection number with the subvariety is 0. So we get a holomorphic sphere which misses that subvariety. Such holomorphic spheres, you can prove, are always constant. Therefore, this kind of bubbling cannot occur. Okay, should I just say that again? So suppose that I have a sequence of holomorphic disks. Suppose they bubble off a sphere somewhere in the middle. That is to say, I have a one-parameter family of holomorphic disks, and in the end I get a holomorphic sphere which meets this. So they limit to a holomorphic sphere and a holomorphic disk which meet at a point. Then just consider the holomorphic sphere alone. This holomorphic sphere, on the one hand, its intersection number with Vz must be equal to 0. Because this intersection number with Vz is a topological thing, and it's additive. So the intersection number with Vz of this sphere plus the intersection number of Vz with this underlying disk must be equal to 0. But both of those quantities are non-negative because Vz is a holomorphic subvariety and both of these are holomorphic subspaces. Therefore, the intersection number of Vz with that sphere has to be 0. And now there's a calculation that you can make, which is that pi 2 of the G-fold symmetric product is always isomorphic to Z, at least if G is bigger than 2. And the representative has non-trivial intersection number with this cohomology class Vz. So it follows that this holomorphic sphere must represent the homology class 0. Therefore, it must be constant. Therefore, this bubbling didn't happen. So this sort of end cannot occur. And one then has to argue about these kinds of ends. So I don't want to go into that, but one can make a similar argument over here and prove that these kinds of ends contribute a total of 0 to the count in d squared equals 0, and hence this is a chain complex. Now, let me just say a few points regarding Saul's question. And that is that again, in order for this differential to make sense, we have to look at those phis such that the dimension of this moduli space is equal to, should also equal 1. And when I say dimension of that moduli space, I mean a formal dimension. That is to say, the moduli space itself may well be empty, and yet formally its dimension is equal to 1. Now this is I realize, a confusing point at first, but let's just think about finite dimensional Morse theory. In finite dimensional Morse theory, here are 3 index 1 critical points, and here are 3 index 0 critical points. And the dimension of flows from here to here is 1. This dimension is 1. But formally, the dimension of flows from here to here is also equal to 1, because the dimension of the space of flows of gradient flow lines is always the difference in the Morse index between the two critical points. Now, you can say this explicitly, which as follows. What is the formal dimension of the moduli space of flows from here to here? Well, it should be the dimension of flows from here to here is 1. The dimension of flows from here to here is also equal to 1. So therefore, the dimension of flows backwards is equal to minus 1. The flows from here to here is equal to 1 as well. So we see that sort of this quantity is supposed to be additive under juxtaposition. So this dimension, let's call this mu of phi. Mu of phi is supposed to be additive if I stick two flow lines together. And therefore, since this is 1, this is 1, this is 1, this is 1 minus 1 plus 1. This would be 1 as well. So this in practice is the way one computes mu of phi. In fact, mu of phi has a topological interpretation as a winding number. But in practice, it is often useful just to know this general property and a few model cases. Okay. All right. Okay. Is everything clear so far? Are there any questions? Okay. So let's look at that chain complex that I wrote up there. Well, there's an obstruction to, I said phi is in pi 2 of xy. But in real life, there's often an obstruction to finding any such phi's in pi 2 of xy. So there's an obstruction to finding Whitney disks. And the obstruction is as follows. Here's say T alpha and here's T beta. I want to connect x to y. Well, T alpha and T beta are both connected spaces. So what I can do is I can just draw an arc from x to y, and I can draw another arc from x, which lives entirely inside of T alpha, and I can draw another arc from x to y, which lives entirely inside of T beta. And that way I get a closed loop in this g-fold symmetric product of sigma. And, well, if that closed loop okay, how should we say this? So if we have a disk that connects x to y, then I can look at its boundary, and that gives me one that splits into a pair of such arcs, which of course are null homotopic in the g-fold symmetric product. Conversely, if I can connect x to y by any old path in T alpha, and then any old path in T beta, then I get some path in the g-fold symmetric product, and we can ask whether or not that's null homotopic. Well, that loop in the g-fold symmetric product is not actually uniquely defined. There's an indeterminacy. I could have chosen a different path from x to y. But if we look at this path modulo that indeterminacy, we get an element of the first homology of the g-fold symmetric product of sigma modulo the first homology of the alpha torus plus the first homology of the beta torus. So given x and y, there is an obstruction, epsilon xy, which lives in this group. And it's defined, let me just say it again, by take any old path in T alpha that connects x to y, and any old path in T beta that connects x to y, and look at that closed loop in this space. And clearly, this element must be 0 if x and y can be connected by a disk. So if pi 2 of xy is non-empty, then epsilon xy must be equal to 0. Okay? And now, here's an exercise if you like. Well, this is not really an exercise. It's a fact that the first homology of the G-fold symmetric product of sigma is actually isomorphic to the first homology of sigma itself. And the T alpha, you can think of it as the image of H2 of the alpha handle body plus the image of the beta handle body. And this quotient in turn is isomorphic to the first homology of y. That is to say, there's an obstruction to connecting x and y, which lives in the first homology of y itself. This obstruction can be described much more concretely as follows. We can think of our Heegaard diagram in terms of Morse theory. So that's to say, suppose I have a Heegaard diagram in a three-manifold can be specified by a self-indexing Morse function with G index 1, G index 2 critical points, and a single index 0 and index 3 critical point. Let's say I've got G index 2 critical points, all of which take value 2 under our Morse function. I've got G index 1 critical points, all of which take the value 1 under our Morse function. And I've got a single index 3 critical point, single index 0 critical point. If I look at the sublevel set of the number 3 halves, I get a handle body. If I look at the superset of 3 halves, I get another handle body. And that's one way of thinking of Heegaard diagrams. And now, what is our alpha torus? The alpha torus is the descending manifold of the index 1 critical points, gradient flows that come out of the alpha, out of the index 2 critical points. Those meet the mid-level in G circles. Those are our beta circles. And I look at the space of flows that go into my index 1 critical points. Those are the alpha circles. And an intersection point between the T alpha and the T beta then is a G tuple of gradient flows, which connect all the index 2 and index 1 critical points. This is another way of thinking about what the generators of our chain complex are. They're G tuples of gradient flow lines that connect all the index 2 and index 1 critical points. And now there's an obstruction to connecting two of those. There's an obstruction. This obstruction epsilon xy can be thought of as follows. We want given, so T alpha intersect T beta can be interpreted as the set of G tuples of gradient flow lines connecting all the index 1 and 2 critical points. Let's call these simultaneous trajectories. So a simultaneous trajectory in the three-manifold is, if you like, it's a one-chain with whose boundary lives inside of the index 1 and index 2 critical points. The difference of any two simultaneous trajectories, therefore, is going to be a closed loop in the three-manifold. And you can sort of unwind all the definitions that I've given so far to convince yourself that that closed loop is precisely this obstruction epsilon xy. Okay? This could be thought of as an extended homework assignment. So this, under this isomorphism with h1 of yz, epsilon xy is the closed loop in y obtained by juxtaposing the trajectory simultaneous trajectory of x and y. Okay.
As an element of H1?
As an element of h1 of yz. And by juxtaposing, I mean you have to subtract the second one. Okay? So this whole story is meant to convince us that our chain complex, which I wrote down, and now I'm going to write it down a million times, naturally splits into a sum of chain complexes. It splits into different summands, and each summand, the set of summands is an affine space for the first homology of that three-manifold. This chain complex CF, what did we say, intersection number of phi with VZ equals 0. CF hat of y naturally splits into CF hat of ys, where S are these equivalence classes of intersection points. We say that two intersection points are equivalent if their epsilon difference is 0. And the set of such equivalence classes has a different, any two equivalence classes has a well-defined difference, which is now in the first homology. Now, in fact, there's a very pretty other set. There's a very pretty affine set for the space of first homology of the three-manifold, which is called the set of spin C structures on the three-manifold. So let me make an aside, and that is let Y be an oriented three-manifold Y is a closed-oriented three-manifold, then we can look at vector fields, V. So consider the set of nowhere vanishing vector fields over Y, modulo the equivalence relation that V1 is said to be equivalent to V2 if V1 restricted to Y minus a ball is homotopic to V2 on Y minus a ball, where B is some ball in three-manifold. So there's an equivalence class of vector fields on the three-manifold. And this set is naturally an affine space. Affine space modeled on the two-dimensional cohomology of the three-manifold with Z coefficients. So let's just think for a minute why that's true. The tangent bundle of an orientable three-manifold is always trivial. If you choose a trivialization, you can think of a nowhere vanishing vector field as a map from the three-manifold to the two-sphere. And this equivalence, and what is a space of homotopy class that maps from a three-manifold to the two-sphere? Well, that can be quite complicated. Remember, there's a Hopf map. For example, for the three-sphere, the space of homotopy classes of maps from the three-sphere to the two-sphere is isomorphic to Z. But in allowing myself to puncture the ball, I've just killed the Hopf invariant. So all that's left is the pullback of that two-dimensional cohomology class in the two-sphere. So for that reason, this space has just been identified with the two-dimensional cohomology of the three-manifold. But in order to make that identification, I needed to fix a trivialization of the three-manifold, of the tangent bundle of the three-manifold. And that's why this is only an affine space modeled on H2 of yz. So I realized that I didn't write this argument up on the blackboard. So we can view this as a homework problem. With a hint, with an oral hint in class. Okay? But this set, this can be thought of as spin C of the set of, this is the space of spin C structures on a 3-manifold. Now, there are more classical definitions of the space of spin C structures on a 3-manifold, but this is equivalent to them, and this point of view has been espoused by Turayev. So, if you want to see why this is the same, you should look at the collected works of Turayev. Okay. Now, that's all fine and well. I've erased everything. What I'd like to now argue is that actually this chain complex splits naturally according to spin C structures. And the way that works is I chose my additional reference point Z. The reference point Z I asked not to live on the alpha or the beta circles. Therefore, it gives us a preferred gradient flow line that connects to index 3 and index 0 critical points. And now we have some other simultaneous trajectory that connects index 2 and index 1 critical points. Well, I claim that to this data we can construct a nowhere vanishing vector field on Y. And the way we do that is we just take a little regular neighborhood of our simultaneous trajectories and also of this fixed gradient flow line that connects to index 3 and index 0 critical points. And I now have a collection of 3 balls in our 3-manifold. And in each 3-ball, I have what we're going to look at is we're going to look at the gradient of F. The gradient of F vanishes nowhere, does not vanish outside of this sort of regular neighborhood that I've drawn. Therefore, it defines for you a nowhere vanishing vector field out there. But on the interior, we have vector fields which do have pairs of zeros. So we have the index 2 and the index 1 critical points. Those are both vanishing points for the gradient flow line of F. What we do is we just excise this regular neighborhood and replace it with a 3-ball with a nowhere vanishing vector field in it, which you can do because the indices of these two gradient vector fields cancel. So you can just delete these 3 balls and replace them by 3 balls which have nowhere vanishing vector fields inside of them. And in that way I've just associated a nowhere vanishing vector field to a simultaneous trajectory. That is to say, we have map SZ from simultaneous trajectories into nowhere vanishing vector fields on the 3-manifold. However, there's a choice. The choice belongs to how we filled in that nowhere vanishing vector field over here. And if we want to get rid of that choice, we divide out by the indeterminacy, and in that way we get a map to spin C structures on Y. Okay. Is this clear? Do I need to say this again? Do I need to write this in words? How many people want it written in words? Oh, that's too bad. Okay. You can go so much faster if you don't write anything down. So, all right. Given an element in T alpha intersect T beta, we associate and also recall that we have having fixed Z in sigma given as element of T, X and T alpha intersect T beta, we can associate a nowhere vanishing vector field over Y as follows. Take the gradient of our Morse function associated to which we're associating our Haggar diagram, take the gradient of F and modify it in a neighborhood of the simultaneous trajectory belonging to x and also the unique flow from index 3 to index 2, index 0. So we now have a G plus 1 tuple of gradient flow lines that connect all the index, that contains all the critical points of gradient of f. So we take the gradient of f and we modify it in the neighborhood of this G plus 1 tuples of curves, so that the new vector field vanishes nowhere. The fact that this can be done is a local calculation. You just, if you have a ball, and inside the ball you have a gradient flow. Sorry, you have a Morse function in the ball with an index 2 and an index 1 critical point. Then, if you look at the boundary of the ball, you have an then you have a different vector field which agrees with the gradient vector field on the boundary but which vanishes nowhere. Somehow you bring these two critical points together and they cancel. They don't cancel as critical points, but they cancel as zeros of the gradient vector field. And similarly for index 3 and index 0. So this can be done. And in that way, if you look at the equivalence class of that vector field, you get this element sz of x in spin c of y. And the statement is that in that way, the chain complex naturally splits according into spin C structures on the 3 manifold. So I suppose, again, there's a kind of formula that one should check, which is the SC of x minus SZ of y is equal to the epsilon is, well, I said that spin C structures in affine space for two-dimensional cohomology. Well, the statement is that the difference in the two spin C structures is Poincare dual to the curve epsilon xy, which was the obstruction of the existence of the disk. And in that way, we can see that this chain complex splits according to spin C structures. Okay, this is all fine and well and abstract and so forth. Maybe we should bring it to life with at least one example. Consider, well, let's start with the simplest thing, which is S3.
Could you explain some of that? So the choice of Z moves around the affines when you changes the identification with the...
Yes. So you have to fix the Z at the beginning of the day. So here's a Haggar diagram for the 3-sphere with a pair of, here's alpha and here's beta. So we've written down now this is a Haggar diagram for S3, and there's a single generator, there's no differentials, so we see that the Floer homology of S3 is isomorphic to Z. Okay, that's fine and well. Let's do a more interesting example. And that is what 3-manifold is this a Haggar diagram of? What? What's that? Okay. Yes, it's a lens space. Which lens space is it? What's that? 2-1, right. This is the lens space L21, or in other words, it's RP3. How many intersection points do you see? 2. x1 and x2. And now, here's a golden question. Can we connect x1 and x2 by a Whitney disk? Okay, to answer this question, let's pass the universal covering space of this picture. Okay, wonderful. So this is what the universal the universal covering space is rather bigger, but it looks loosely like this. We have our reference point Z sitting here, say. And what I'm asking is there a disk that, in the quotient, is there a disk that connects x1 and x2? Well, there can't be, right? Because if there were, you could lift that disk to the universal covering space, and we'd get a disk whose left arc lives in the blue line and right arc lives in the red line, and it connects x1 and x2, but they don't. These things go far apart. So the epsilon, these two intersection points cannot be connected. And so epsilon of x1 and x2 is actually equal to the generator of the first homology of RP. And more generally, if we wanted to draw a Haggar diagram for LPQ, we would draw a P over Q curve, and there would be P intersection points, and all of them would live in different homotopy classes. Maybe let me try to convince you once again that this epsilon difference is the generator. And the way to see that is, let me just draw this picture again. So here's x1. I'm just drawing exactly the same picture again. Maybe for no reason at all. Indeed, I'm sorry. So what have we done? We connect x to y by any old curve in the blue arcs, and we connect x to y by any old curve in the red arcs. And that way I get this single loop in the torus. But that single loop in the torus is a generator for the first homology of RP3. Okay? Because okay. So HF hat of the lens space LPQ in general is equal to Z to the P, and the different intersection points all live in different homotopy classes. Okay. All right. Well then, I think I've perhaps filled the time slot. Are there any questions?
What if there's no intersection points?
Then the Floer homology should be 0. But there's a subtlety here, and maybe I should address this subtlety. It's a good question. The definition that I've written up really only works for integer homology sphere, or for rational homology spheres. For more general kinds of 3 manifolds, let's look at, for example, S1 cross S2. S1 cross S2 has a Haggar diagram like this, but it also has a Haggar diagram like this. Okay, so if you take this curve all the way around like this, you get 2 different equivalence classes. So, but the point I want to make really now is that when B1 is bigger than 0, then we must use special Haggar diagrams to calculate the So let me pass that point off to the main teacher of this course. Okay, are there any other questions which I could dodge?
So you didn't actually answer my question way back when, which is, so I believe, even if I believe that it's a chain complex at the ends,
Yes.
I still don't know how to actually calculate, right?
Right.
Even in the toy example, where there's just like the circle and the line going through it, maybe there's some other bizarre holomorphic disks, which I just don't see.
Oh, no. So in the circle and the line, there can be no sort of, I mean, in these examples in the plane that I drew,
I mean, you could slip them both, but you can't slip them both.
pardon? No. In the examples in the plane, you can check that I've told you all the holomorphic disks. This follows from the open mapping theorem. So you can just check that. So let's take the broken heart example. You can see that any holomorphic disk that connects X to Y must have as its image, the closure of this image must be the heart itself. It must be some slit. Now, those are very special cases. So in the plane, we know how to calculate Floer homology. But in general, on a G-fold symmetric product of sigma, that's a very important and deep and difficult question to actually calculate this chain complex. And there are tricks, there are ways around it, there are calculational tools, but there's no answer. Somehow, I feel with this theory that we're at the stage that they were in the beginning of the 20th century. If you know about harmonic forms, and you try to calculate the homology of a manifold by calculating all the harmonic forms on it, calculating all the harmonic forms on a manifold is a difficult thing to do. But we have now singular homology, which allows you to calculate these groups. Presently, there's no analog of singular homology, or Heegaard Floer homology. So this is something that we should all find as a motivating problem. Okay. All right, maybe I'll stop.